Hello, everybody. This is Bernard Scheider, and you've hopefully entered my advanced presentation on purpose. Just 1 minute, I'll bring up my slides, and then I can start. So, okay, hello. Thank you for showing up, all of you. My presentation today, that's the advanced training for swak4Foam and PyFoam. The specific topic is swak4Foam and PyFoam for solver developers. But the things that I present here are, of course, useful for more advanced users as well. So let me go. So the purpose of this presentation is basically, the primary purpose of this presentation is to show you how swak4Foam and PyFoam can help you if you're doing some OpenFOAM development on your own, and also how to find problems in your cases. Some of the highlights, that most useful stuff that you will learn here is getting post-mortem dumps for failed cases. It happens to all of us that you start a case, the case crashes with a floating point exception or something like this, and then you want to find out why did this happen. And the other thing is, of course, you run the case runs okay, but you think it's running very long, and you want to find out which parts of the solver are using most of the CPU time. The intended audience for this is people who develop their own stuff in OpenFOAM. Some of you do it for a living, some of you do it for their thesis. You should know a little bit about swak4Foam and PyFoam, but not too much. For instance, yesterday's training is absolutely sufficient. But the things that I'm going to present here are interesting for non-developers as well. So who am I? I'm Bernard Scheider. I have been working with OpenFOAM since it was released as OpenFOAM. I am what the OpenFOAM core developers call an enthusiast. My involvement with the OpenFOAM community is that I'm the janitor of the OpenFOAM wiki, and I'm the author of the 2 packages that I'm going to present here, and I'm doing some other minor stuff as well. But all this is collateral damage to the work that I regularly do. I work for a small consulting company called Heinemann Fluid Dynamics. We do solver development and simulations. During this presentation, I will take the point of view of a guy called Ignaz Gartenschirl. Ignaz Gartenschirl is a CFD developer. He was one of the first and most enthusiastic users of swak4Foam and PyFoam, and we may call him by his first name. And people from Austria can tell you what his last name means. Some time ago, Ignaz stopped doing presentations on these things. He had changed his career, but now he is back, and yeah, by popular request, people asked that my presentations should have an Ignaz in them again. And he is now working for a company that's called Warm Rooms Limited, and they want him to develop a new combustion model. It's patented, but it's unphysical, but okay. So this is a trigger warning. There are some unrealistic physics in this presentation. The reason is having realistic physics is either it's already implemented in OpenFOAM, or it's rather complicated, and that's beside the point of the exercise. So the combustion model is simple, and it doesn't resemble any real physics. Don't use it, don't reference it. You may laugh about it, but not into my face. We are working with two packages that I already said. One of them is PyFoam. PyFoam is a library for manipulating OpenFOAM cases and controlling OpenFOAM runs. It was written in Python. It's designed to have as little dependencies as possible. And it's best known for a couple of utilities that that use the library beneath it. It strictly does stuff from the outside, so it's completely agnostic to which OpenFOAM version you're using. It just manipulates the files, the case files, and it reads the output of OpenFOAM, but it doesn't link to it in any way. All the utilities start with PyFoam, so if you have a decent tab completion in your console, then you just type PyFoam, type tab, and you get a complete list with all the utilities that are there. There are, I think, approximately 30 utilities. And every utility has an help option that helps you, that gives you information about the utility, what the options are, and usage examples. swak4Foam is, swak stands for Swiss Army Knife. It's a collection of libraries and utilities whose goal it is to make it unnecessary or less necessary for you to write C++ programs for simple stuff like setting boundary conditions, setting initial conditions, and things like these. And the core of swak4Foam is that it's a collection of parsers. A parser is a program that reads a text and interprets it and does some things. And basically what it does is it reads expressions like the one above. It evaluates the expression and then does something with the results. Before we start, there are going to be some command line examples on the slides. If there is only a single line, then you will see this less sign, and then you will see and what you should type in. Bigger examples are in such a gray box, and there you see the input that you did. The input that you did is going to be in blue, and the output of the OpenFOAM or any other program is going to be in black, and you will see line changes. For this presentation, or to replicate the results in this presentation, you will need a machine with an OpenFOAM 2012, that's the ESI fork. You will need swak4Foam, PyFoam, and a text editor. The first and the last, I think that should, if you're developing, then you should have these already. There is a Docker image for with basically all the software that you need for this pre-installed, and there are also the example files that of the examples that I'm going to show you. They are also inside of this Docker image. So if you have Docker on your machine, then you can try the things that I'm showing you here without any further software installation. There is no paraview in this Docker image because paraview in Docker images is a nightmare. Pulling the Docker image is basically you can pull it with this command. The command up here. That's the name of the Docker image that we're going to use. Then you get a special, there's a script that makes this Docker image easier usable, and basically starting a container, you just call the script and tell it the name of the Docker image. And then you're in a shell inside of the container. The directory that you're inside of the container is the directory on your host machine that you started it from. So it's quite easy. So basically everything you do in the directory that the shell is in will later end up on your machine. So you can store your intermediate results there and things like this. And yeah, the Docker image can read and write the same files as your host user. Yeah, that's the way, for instance, it would look like on one of my machines. The test user is the name of the user on the host, and you see that you can execute stuff in the Docker machine, and these changes will end up on your machine. Yeah, I noticed that when I tried the examples in the Docker machine is that there is one directory in the Docker machine that you're not allowed to write to. With these two commands, you've got to do that inside of the machine. There's no need to issue a password. You make that directory writable to yourself, and then you can, for instance, compile the solvers that I've shown. And the examples are inside of the root of the /examples folder in the Docker container, or you can download them from this URL. Okay. Ignaz wants to make sure that PyFoam is running. So usually what he does is he runs PyFoam version, and there is all the necessary information that, for instance, I need to support you for if you have problems with PyFoam, and the PyFoam version, it can be seen down here. And to make sure that swak4Foam is installed, you just say, okay, funky set fields, and you should get an error message with the regular OpenFOAM output, and the release of and the swak version is printed down here. Okay, so now let's get to the interesting stuff. As I said, trigger warning. Again, please, if you're easily disturbed by unrealistic physics, please go away. There are 4 other very interesting training presentations. So Ignaz needs a combustion model. Basically, what his boss specified is they want to develop a heating fluid. That's a fluid that flows into the room and starts heating itself up after some time until a maximum heating rate is reached, and that fluid is supposed to regenerate itself when it's very warm in the room. Nobody knows how to produce such a fluid, but they said, okay, just first make the simulations. We will get to these little details later. So these are basically the equations that I'm going to implement then later for this. Basically, I'm just going to add a source term to the regular energy equation where it says, okay, there's a heating energy, and there's the heating energy, the reaction rate R. The heating energy is a constant, and basically this reaction rate is 0 below a certain fluid age. Above a certain fluid age, it reaches the maximum temperature, and between these two ages, there's a linear interpolation of the reaction rate. The fluid age is calculated like this. Basically, it's a transport equation without a diffusion term, and it adds the dimension of tau is time, and it basically adds 1 second per second. So it increases the age of the fluid as it moves through the things. And the last thing is basically is a decay term where the fluid age regenerates once we have reached a threshold temperature. So at first, some words that are not developed by me, that's basically the stuff that OpenFOAM offers you if you develop in OpenFOAM. OpenFOAM is still very much developer oriented. This is quite nice for developers because there are also some things that help you very much. It has some very useful things built in, but some of them have to be switched on, and I will show you this how to switch them on now. If you're doing any development, then probably you have already heard you can do it just with the regular optimized version of OpenFOAM, but it's very, very good to have a debugged version as well. Basically, the distinction between the two of them is the WM compile option. Usually you have opt. This is the usual thing, that it's compiled to be optimized for speed. And then there's the debug option that is for developers. That's terribly slow. And so, but why is it slow, and what are the advantages of this is, there are additional debug symbols in the code. So if you have stack traces, so you can use a debugger on your solver. And if you have stack traces, then you also get line numbers and source files where the problem occurred. And the most important thing is that almost every bracket operation on fields and lists is range checked. So if you try to access a list outside of its range, then these operations will fail. And that's because in the regular solver, in the opt version, this is not checked. So if you access something outside of the list, then if you are lucky, then you get a segmentation fault. And if you're unlucky, it just works outside of the list, and it's possible that you get weird bugs. So the debug version helps you very much so I think 80% of all the bugs you can make in OpenFOAM, the debug version will tell you about. And even if you say, okay, I'm such a good developer, all my programs are bug-free, my advice is to always have a debug version, and before you release your program to anybody else, compile it in the debug version and run it there. You'll be surprised how often you find a bug that you didn't think about. One thing is that there is a environment variable foam abort. Set that one, because that way every time OpenFOAM reports a fatal error, this is automatically escalated to an abort, and you will get a stack trace, which makes it easier for you to find the problem. Then also, I think usually this nowadays is set up per default in most OpenFOAM versions. That's the environment variable foam signal floating point exceptions. Basically, without that option, it's possible, that depends a bit on the compiler and the machine you're on, that for instance, you have a division by 0 and your program says happily, okay, this is infinite or not a number. I'm going to happily go on calculating with this infinite value. And with this environment variable set, you're sure that your program will crash when it gets something numerically stupid. And the other environment variable together with this is foam set not a number. Basically, what this does is OpenFOAM uses its own memory allocation routine, and that memory allocation routine gets memory and then fills the memory with not a number. So if you have no other code that initializes that memory, then if this memory is used for calculations, you get a floating point exception and it fails. This helps you track problems where you didn't initialize some memory, and usually there's random stuff in here, and with random stuff you can be unlucky and the program says, okay, I'm going to do this, calculate with this random stuff. With this foam set none, you can be more sure that you have no uninitialized memory there. The story about the brown M&Ms, Google it, it's quite instructive. As I said, one of the coolest features in OpenFOAM that's there since the beginning are stack traces. Basically, when you when you run abort or when an exception is raised, when a signal is raised, then you get this stack trace, and the stack trace means, okay, you start with the innermost, and you work yourself to the bottom. Basically, the top stack frame is here where the actual OpenFOAM program is started. Oh no, here where it started. And between that, you will find the location where you have your error. In this case here, it's in number 3. Usually you can ignore the top 3 stack frames because these are administrative stuff by OpenFOAM. Yeah, and one of the things that you see here, so basically the stack traces were here all the time. One of the nice things you see here is that it also tells you, okay, it tells you, okay, in this line of code, in this file, in this line of code, did the problem occur? And one of the ways is to basically, if you think it's your mistake, then you go through the stack trace and find from the top, find the first source file that is yours, and then you check what is happening in this line of code. Just a pat on my back. As I said, stack traces were there all the time, but one of my first patches contributed to OpenFOAM was basically to print the source file and the line number as well. So now there are some things where PyFoam can help you with development. One thing is that when you're developing, it's not unusual that you have more than one foam version. For instance, you want to compare how different forks of OpenFOAM do different things. You want to reproduce results that you did in your old solver because you're porting your solver to a new version, and you think that you have the results differ. Yeah, and so PyFoam helps Ignat seamlessly work with different versions, because usually what you usually do if you want to switch to a different version, then you have to source the bashrc file of that version, and then the shell is in that version. And once you have stopped working with that version, you have to switch it back. So basically, this is permanent. But PyFoam has the PyFoam utilities that run solvers have a option foam version where you say, okay, I want to run, I know I'm working with 2012, but I want to run the check mesh of version 8 because I think the check mesh in version 8 has stuff that the current version doesn't have. If you specify an unknown version, then PyFoam will give you this error message with all the OpenFOAM versions that it found that it can switch to. And basically what this does in the background is it does the switching as above, but it just does it during the execution of the program. And then when the PyFoam runner utility ended, then you get your old version back. But what it's most important for is the force opt and force debug version. With that, you can switch to the proper WM compile option. These options insist that you specify which OpenFOAM version to use. If you don't want to retype, okay, I'm using this one, you can use a current foam version. With that, PyFoam knows, okay, switch to the debug version and do it with that. So yeah. So you can switch to the debug version, for instance, to run SimpleFoam in the current one, or you can switch to another OpenFOAM version because there is a utility there that will be released 2 years in the future. And there is PyFoam execute. PyFoam execute basically is similar to the PyFoam runner utility, but it doesn't require that there is an OpenFOAM case there. It's nice for executing non-foam commands, and with non-foam commands, for instance, I also mean wmake. So basically, if you have in your mysolver directory, if you have your source code there and you want to compile it as in debug mode, then you say force PyFoam execute, force debug, wmake, and mysolver, and it will compile it. Or what happens sometimes if you compile OpenFOAM versions yourself, the current version doesn't have PyFoam installed, then basically, for instance, to install PyFoam or to execute PyFoam from another version, then you say, okay, PyFoam execute, use PyFoam from OpenFOAM 7. And also what PyFoam does is it does some simple control dict modifications. Basically, it modifies the control dict, then it runs the solver, and once the solver finished, it reverts the changes. So the advantage of that is that you don't have to edit control dict yourself, and then you forget that you edited it, and suddenly you say, okay, why is it filling up my disk with loads of data? The 2 most used options for that is, for instance, if there is a problem during the startup of your solver, then you say, okay, write all time steps. So that modifies control dict in such a way that every time step is written to disk. And then you can say run until, and you set and that sets a different end time because you don't want to run it through the whole thing. Then for instance, here it says, okay, run until 1,000th of a second, but until then, please write me every time step. So the first thing that really Ignat's interest is prototyping. Ignat says, okay, it's an interesting concept, but at first I want to show see what the numerical problems are with this flow time equation. So I want to prototype that in a solver before I start touching any C++ programs. And swak has a number of tools that are not specifically designed for prototyping, but that can be used for prototyping your solver or your boundary condition or whatever you're developing. I'm just going to show you how to prototype simple transport equations, for instance. So Ignat wants to add a flow time to an existing solver, see how that works. And for that, there is a function object solve transport PDE in swak4Foam. There's a similar function object in recent OpenFOAM versions that was written after I developed this. I still use this one because it's more flexible, as you will see, because I can basically use expressions for everything. So it's time derivative, divergence, or convection, the convection term, diffusion term, and then you have the source term split into 2 parts. One is explicit if it doesn't depend on your variable, and the other one is implicit if it depends on your variable, because that might improve things numerically. And so basically what Ignat wants to check this with is this flow time equation, where he only has a convection term and a very, very simple source term that basically is 1. He wants to implement that, and he uses as a base case, he uses the PITS daily from the tutorial cases for row pimple. It's simple. It's sufficiently non-trivial and it's not too big, so you can easily do experiments with it. So to add the transport equations, he goes to the control dict and adds a function object there. Basically, the function object is a solve transport PDE. Then he says, okay, I'm not going to solve this steadily. For rho in the transport equation, use rho. You will find that in memory. That's the usual thing. The diffusion term should be 0. The source term, the explicit source term, is 1. That's what we had. And for convection, use the field phi. And yeah, that's basically it. And also solve this at every time step because for instance, sometimes you want to have a steady solution that you only solve in the beginning. Then you set this different solve at here. Also, and what is also important is you have to specify a field name. And then swak4Foam looks for that field in your initial directory, loads it, and uses the boundary conditions there. And of course, the initial conditions. And for this thing it's basically walls don't change it the flow time, and on the inlet the flow time is 0. Yeah, that one I explained. So basically now Ignaz starts this. For the temperature, you get the usual behavior that this tutorial case gives you. So you have this temperature, for instance, in the beginning, and after it calculated for a tenth of a second, then you have this temperature distribution. One thing that can be very helpful during development that I didn't discuss is basically having regular graphs with the important properties or fields of your simulation. Looking at these graphs, sometimes, for instance, when you look at how temperature evolves over time, you know, without opening ParaView, that this case exploded, and you can stop it because there will be no valuable information, and then you can start debugging why this happened. But for this, ordinary swak4Foam and PyFoam is sufficient. Look at yesterday's presentations, for instance, how I set up things like these. Yeah, the graphs follow. I think the last slide was in a different order than I thought. Okay, but for instance, here that's the first nice thing. Here we have the flow time in the beginning. We see that we have a flow time of 0 that comes in. That the flow time rises. And what you see in this region is that we have a high flow time. That is because the flow time here started at 0, and we calculated for 100th of a second. So in this whole region, the flow time is 100 because of the source term. In the beginning, when basically the flow has reached the outlet, then we get this flow time distribution. You see that you have a flow time of approximately 500th of a second here at the outlet, and higher flow times at the boundary. We're going to get to these later. So these are the graphs that I was talking about previously. So what you see here is that basically the solver started at 300 degrees, and then you have temperature fluctuations here. It's quite valuable to look at these things before you start your own development, because you see, okay, there are temperature fluctuations already in the base case. So if I see some in my later calculations, they are not my doing. So that these are this, for instance, that's a graph for the flow time. what you see here, I plotted different. I plotted the flow time in the whole domain, and I plotted and I plotted it on the outlet. What I like to do with things like these is look it up on the other slides. Is have a weighted quantile, I call it. Basically, I have the minimum, and then I have a 1% quantile, which basically says, okay, please give me the value where 1% of the volume of my domain has a lower value than this. The nice thing about this is, especially with, for instance, if you're monitoring the pressure, sometimes you have very, very tiny cells that have a higher pressure than the other cells because they have a problem with the pressure equation. And these are not really representative. And by using such a quantile, you can clip them off and you get something that is a more realistic maximum value, or a more stable maximum value. And you know, okay, in general, the case is doing all right. So what we have seen before on the graph with the flow times, or not on the graph, when I shown you the converged flow times, we've seen that there were very high flow times near the walls. That is understandable because near the walls there is a very low or almost zero velocity. Flow time is only transported by convection, not by diffusion. So it's very hard for the solver to transport out the flow time. So what Ignaz does is, okay, it says, okay, I'm just for the fun of it, I'm trying to limit the flow time. He replaces the source time with a constant value of 1. He replaces it with a conditional flow expression. Conditional expressions, you probably know if you have done some C, C++, or Java. It's basically, there's a condition, then there's a question mark. If the condition is true, then the stuff between the value between the question mark and the colon is used. And if this expression is failed, then 0 is used. So basically what this says, if the flow time at this location is smaller than 200th of a second, then increase the flow time. If it's bigger, don't increase it. And now when we run the case, flow time looks like this. You see that it increases until it reaches 0.2, and afterwards it stays at the same flow time. That is, for instance, is also interesting for Ignaz because now he knows, okay, at 0.2, that's a nice threshold. 0.02. That's a nice threshold, for instance, to start the combustion. Then the flow has already reached the interior, and it's nice to start that one. And we also see for the modified flow time, we also see that now that the graphs are a bit different. The maximum flow time doesn't grow unbounded, but it stops here at approximately 0.2. There are some excess flow times because of numerical stuff, and the average flow time is also stops at this region, at this value. In addition, there's also a solved Laplacian PDE that solves a heat conduction diffusion type problem on your region if you need that. The reason why I'm not using the regular transport equation is that it does some things differently. So yeah, and other things for prototyping, I'm just going to go over these quite quickly because I will discuss them. I discussed them in other presentations. Yeah. For instance, if you want to develop your own boundary condition, at first one possibility is to test it in Groovy boundary condition to check whether something like this boundary condition works. Sometimes you are satisfied with what Groovy boundary condition gives you, and then you can scratch developing your own boundary condition, which always has the advantage of this is if you have a Groovy boundary condition in your cases, then you can easily, as soon as I ported swak4Foam to a new OpenFOAM version, then basically your boundary condition is automatically ported to that OpenFOAM version. If you develop your own boundary condition, you maybe have to modify some things in the boundary condition because things might change in the boundary condition. One of my design goals for swak4Foam is to have things backward compatible. So I try not to modify the expression syntax anymore, even if I think that now 10 years later some things would be better otherwise. But I don't do this because I don't want to break your old cases, and more importantly, I don't want to break my old cases. But for an example to use boundary conditions, you can look at the presentation from the Duisburg workshop 2 years ago. There are some fancy things like storing of values, coupling with other parts of the models, and time delay of boundary conditions. Some of these things are not easy to implement if you do it yourself, or not trivial. You're grown people, you can do it as well. Additional source terms, if you have a OpenFOAM fork that uses VF options like foam extend or DSI release. No, not foam extend. Foam extend doesn't have VF options. All the other foam forks have this nowadays. Then you can easily add your own source terms to most of the equations in OpenFOAM. And for instance, in the presentation State and Solution in 2017, a workshop in Exeter, I show how to easily develop a porous filter with particle flow and changing properties, just using swak4Foam stuff and not doing any C++ stuff. So the example case that I've shown you before that you can find in this tar file if you downloaded the tar files, or you find it in this directory in the Docker image. Yeah, before I go on, I'm at halftime. That's faster than I expected, so maybe I will have some time for questions later on. So please feel free to write questions in the forum, in the conference software. Also, there is a little poll where I ask which OpenFOAM forks you use. It would interest me to know what people are actually using, because it's a lot of work porting it to all 3 forks, and I just want to know if it's worth the effort, and nobody is using the foundation fork nowadays anyway. Okay, so now we get to the real interesting stuff. Now Ignaz has seen that the time equation in theory works, and now he starts implementing his own solver. He takes as the basis, he takes row pimple foam. It's a good idea if you want to develop your own solver, and you just to look at the solvers that OpenFOAM already has and extend an existing solver. Unless you want to implement a totally improved new solver scheme, then of course start with your own. But if you want to add some crazy physics to your solver, then start with an existing solver. He uses it, he takes it because it's transient and it solves the energy equations. So basically what he has to do, he only has to add a source term and an equation for the float time. The material for this is basically, that's in two tars. One of them is this road time trigger foam. That's the actual sources of the solver. I'm only going to show you the interesting parts. Stuff like creating fields and reading parameters, you probably already know because you're developing your stuff yourself. And the case that I'm going to use is in the other tar file, and basically both of these can be found in the examples directory of the Docker image. So basically, to the basic solver file, the C file, there are only 3 positions where you have to add something. At first, this line adds the include file where the specific fields that we need for this model are created, and this file reads the parameters that are model specific. I'm not going, as I said, I'm not going to show you these. This is basic OpenFOAM programming. And then I go down in the solver sources, and between the solution of the velocity and the solution of the energy, I insert the time equation, because basically we use this flow time to generate the source term that is later used for the energy equation, and it's best to do that kind of thing before it's used, but after the velocity has been solved for. There is going to be a number of parameters that are read in the read parameters file. That's the reaction start time, the reaction maximum time, the maximum reaction rate, reaction energy, that was how strong the reaction influences the temperature, and then there's the decay temperature and the decay speed for for the fluid to regenerate for high temperatures. We use these variables now here, for instance, in time equation. There's basically 2 interesting things. The calculation of the high temperatures, where it creates a field with the excess temperature. That's the temperature that is higher than the decay temperature. What is done here is basically it subtracts decay temperature from the real temperature, and if it finds that it's smaller than 0, then it sets this value to 0. This is simple, and this is the time equation. Now, the thing that before we implemented in swak4Foam is now implemented here as a regular transport equation in OpenFOAM. Time derivative, convection term, then these are the regular VF options. This is the term that basically increases the time by 1 second each second. And this is the term that implements the decay that regenerates the fluid. And after this equation has been solved, we calculate the reaction rate. So basically, it loops over the reaction rate field that was created somewhere else. It sets the reaction rate to 0 if the time in the current cell is smaller than the start time. It sets it to the maximum rate if it's bigger than the maximum time, and for all cells in between with values in between, it does a linear interpolation between the two. The modification of the energy equation is trivial. Basically, everything except for these 2 lines, the plus and reaction energy times reaction rate times rho, that has to be added. That's the source term we're adding to it. So, and the actual values that were used was here. I said, okay, I use as a reaction start time, I use 0.2. That's what we saw in the previous experiments with the prototyping. And after 0.04, it stops reaction. The maximum reaction rate happens to be 1. Ignaz is still waiting for real materials to arrive from the labs, and so that he gets real values for that. The reaction rate is this, and the reaction energy is this, and the decay temperature, he says, okay, that's 400. That's a bit warm for warm rooms, but he just wants to see, I mean, because it's quite hard for a human to survive at these temperatures, but he wants to be sure that the solver really works. And so now the results that he gets here. You see the flow time. You see that how the flow evolves over time. You see how the temperature evolves over time. So in the beginning, before 0.02. There was no reaction because that was the minimum time. Before that, we have the same fluctuations. If it zoomed in, we'd see the same fluctuations that we've seen in the original solver. And after that, once the flow time increases, it starts going up. We have this decay time at 400 degrees, where it should regenerate the fluid. And we see that this limits the temperature, but to a much higher thing. Also, one thing that we see is that we get quite low temperatures. That one is a bit hard to explain. The physics doesn't explain it. I think that is a numerical artifact. That's basically an escalation of the low temperatures that we saw in the unmodified case. Here we plot the reaction rates. We see that the reaction rate starts here. The maximum of the reaction rate goes to the maximum value of 1 at exactly the time that we expect it to, and then we see, okay, the average reaction rate, and for instance, down here is the average reaction rate. And for instance, this is the 99% quantile. This basically says, okay, 99% of the region have a reaction rate that is lower than the green line. That sometimes is more useful than seeing, oh, okay, the maximum is 1. I mean, that's also useful because it tells us that the reaction rate doesn't go outside of the values that we wanted. Okay, so the results that we see here is this is basically the temperature in a converged state. We see that the flow comes in quite cool, and it's heated up here near the outlet and here in the recirculation zone. And the reason for that is that basically we have a non-zero flow time here. We see that the flow times increase here. We see the high flow times near the boundary that we have seen before. And we see that once the flow is very hot, because of the regeneration, the flow time gets smaller again. And for instance, here we see the reaction rate that is calculated. That's also between 0 and 1. And as I said, there's only 1% of the volume has a reaction rate that is bigger than 0.6 approximately. And we see that it doesn't surprise us very much, that's near the boundary here. And we see that the highest reaction rates are here when the fluid is old enough, but not yet hot enough to decay. And after it decayed, we see much smaller reaction rates here. So I was cheating. Usually when people show their presentations, they cheat, they show interesting results, and the interesting results were not the first results that they had. They had in between, they had terrible solver crashes, they had wrong physical results. And the same happened to Ignaz. Ignaz, when he started, he said, oh, okay, I can make without this decay. I'm setting the decay speed to 0, so that basically there's not going to be a decay. The fluid will leave anyway, and I'll be fine. And then he ran the case and he saw a crash, and he said, okay, it would be nice to see what exactly were the values at the time of the crash and what happened immediately before that. And then from looking at that, I could explain that. One way to solve this would be to tell Open to go into the control dict and say, okay, write out at every time step and use purge write to remove all the time steps except for, let's say, the last 10 time steps. The problem with that is it involves a lot of disk I/O and makes things very, very slow. So what swak4Foam has is a function object, write all times on signal, that is used exactly for that kind of stuff. That's basically, it hooks into the regular OpenFOAM signal handlers. If one of these signal handlers is raised, the function object takes over. It looks through the object registry. That's basically where all fields are registered in OpenFOAM. It looks through the object registry for volume fields, and it writes these volume fields to disk. And after it has done that, it executes the regular signal handler. So basically what you get is, if you have a floating point exception and you've specified, please handle floating point exceptions. If you have a division by 0, for instance, then it writes out all the fields exactly as they are currently, and then you can go to ParaView and look and say, oh, okay, is it because the density became 0 somewhere, or what happened? It also tries to do that for parallel runs, but because of technical details for some OpenFOAM versions, this doesn't work. That's something where I'm always catching up. Then the other thing that would be nice is it's nice to see the crash value, but it would also be nice to see what happened before the crash. And for that, it has this function object has the option to store time steps. So basically what it does is, instead of writing disk data to disk, at the end of every time step, it goes through the object registry, looks for all the fields that are in the object registry, and copies them aside. So it says, okay, currently it's time 0.1. Give me all the fields, give me the velocity, the pressure, etc. And he copies those fields to a separate location. And if, for instance, at the next time step, it crashes, the solver crashes, then it says, okay, I've got the fields for time step 0.1. I'll now write to the directory 0.1 all the values it has there. If it's told, for instance, that it has to store 10 time steps, and if that limit is reached, then it says, okay, let's forget the old 0.1 time step. We're much further. We won't need this anymore. So that is how that would be enabled in a solver. Basically, you say, okay, write all the time. Right. You specify here, write all times on signal. That's the type of the function object. Then you say, okay, store 10 time steps. I'm going to talk about the number of these time steps. Don't go overboard with it. Then it also asks whether to write the current time step. That is important because sometimes certain types of crashes, writing the current time step crashes the crash handler, and that cannot be resolved anymore. So you can switch that off if you have problems with these. And then it says, okay, you can choose when stuff should be written. For instance, here here I switched on everything. I say, okay, write stuff when you have a floating point exception, write when you have a segmentation fault, write if the user pressed Ctrl+C. That can sometimes be nice, sometimes be annoying. Write if OpenFOAM has any error that is not directly related to the field. For that to work, you have to set the foam abort environment variable that I talked about earlier. And you can even switch on with sig quit. You can even tell it to write if you went to the shell and got the process number and killed the process with kill process number, then it will write stuff even then, unless you do the kill with -9. But that's that's more Linux specific. So basically what Ignaz does is he reruns the case that is crashing. He basically, he reruns the case. The case runs until this time. And now when he looks at the directory, he sees, okay, there's the first 5 time steps. These are the regular writes. And here he's got 11 time steps. This is basically, here you see the time step where the solver crashed, so he wrote the results there, and then you see the 10 time steps that are immediately before that time step. And here you see that, for instance, you see the graphs. You see here that the temperature, it crashes. It crashes because the temperature got a very high value on one side, and it also got values of below 0. It got temperatures of below 0 Kelvin. If you measure such a thing in real life, go to Stockholm, Oslo, apply for your Nobel Prize. These are the flow times. These look pretty regular. And for instance, here you can have a look at the results, the temperature before the crash. And what you see is that the very, very high temperatures, that's not immediately by the crash, that's 10 time steps before the crash. And you see that 10 time steps before the crash, you have values of 6,000 kelvins here in the recirculation zone. We will get later to the recirculation zone. That seems to be a source of joy for this simulation. When you're using this function object, beware. It's free, but it uses time and memory. Obviously, because it's copying all the fields that are there, if you specify, you say, okay, save me the last 10 time steps, then it will use 11 times much more memory than it would use regularly. So if you have a case that uses half of the memory on your machine, then you're in bad luck, then you can't use this. But if you have such a Mickey Mouse case like the Pitts Daily case, then I think you can even use record the last 100 time steps. And it uses computation time. You might ask, oh, okay, but it's only copying. Why does it use computation time? The reason is that basically memory bandwidth is usually for CFD cases the most important and most scarce resource. And copying the fields, basically there's not much computation going on, but it needs memory bandwidth. And so sometimes this function object is known to need as much as 10% of the computation time. So only use it if you think your case will crash. Or use it without recording the old time steps. That's of course an option too. Then you can use it for production cases without problems. So one thing that Ignaz noticed is that he gets rather high temperature spikes. If you remember from the regular run, that he got temperatures that went up to 700 degrees Kelvin, and but regularly the temperature is below 600. And Ignaz wants to know why that is. And one of the things is he could look at the graph, say, okay, there's a temperature of 700 at the time 0.135. So I'm going to manipulate the control dict in such a way that I'm sure that this time step is written. But that's quite error prone, and it also uses a lot of computation time, because if you want to investigate another event, then you have to redo all these things. And one thing that you can do is there's a right and end swak expression thing. That's basically, there's a function object that says, okay, if a specific swak expression is true, write everything and end the case. That's similar to the right and end that we had before on Signal that we had before. But we're not going to use this. We're going to use something more interesting, but you can try it as an exercise. And so there's a function object that's called write if swak expression. There are several other write if function objects. You can investigate for yourself what OpenFOAM does there. And basically what it does is at the end of every time step, it evaluates a write condition that you specified. Then it says either if you specify, or it says if any cell has this write condition, is true for this condition, then we write. Or he wants all the cells to be true. That's the other accumulation that you can specify. And you can also, what it also can do is it can store and write times before such event. So if there is a temperature spike in your simulation and you want to catch this with this function object, then you can say, okay, and I want the 10 time steps before the temperature spike, because usually that's where the interesting stuff happens. Okay. And I wrote here cells, but you can use other, you can use evaluate patch values, you can evaluate probes, you can evaluate anything that swak4Foam can probe. And it has basically this function object goes through 4 different stages. The first is regular mode. Everything is fine. The condition is not true. The condition is evaluated and nothing is written. Once the condition triggers, it goes into write mode. Write mode, it writes the current time step, and then it starts and then it looks for a variable that's called write control mode that tells it how long should I keep writing. So basically, should I just write this one time step, or am I interested in the next 10 seconds to be written? That you can specify with the write control mode. After that, there's a cooldown mode that avoids. With that, you can avoid to be the writing to be immediately triggered. If you say, okay, I'm still in the event and I just want to catch the next event, so I'm going to wait 100 time steps before I consider writing anything. That's controlled by cooldown mode. And once cooldown is over, it goes back to regular mode and waits for the event to occur again. And for write and cooldown mode, you can either have a swak expression, you can use a simulation time. That's what I said. So basically, you can use a swak expression. You can say, okay, please keep writing until the temperature dropped below this, for instance, or you can give a simulation time. You can say, okay, simulate for 100th of a second, or just write the next 10 time step and then go to cooldown. So, okay. What Ignaz does, so basically what Ignaz added here now is he said, okay, write the swak expression. He said, okay, if the temperature is bigger than 600 and it only has to be true in one cell, then it's fine. Write it out. he also tells it, okay, store the previous time step and store store 5 time steps. So if that triggers, 5 time steps before that are also written out. The write control mode should be time steps. Please write out 5 time steps after the event as well. And for the cooldown mode, he takes an interval. He says, okay, and then wait 1/1000th of a second before you start considering anything again. So after he has run this, then basically he gets a lot more time steps. So basically you see that this triggered a couple of times. It obviously triggered here at 0.033. There it wrote 11 time steps, then waited, and then again triggered here. Triggered again here. Then there was a regular phase of simulation, and at 0.107, that's where the highest temperatures were. That's the one that we're going to look at in ParaView. So basically, Ignaz opens ParaView and, for instance, looks at the high temperatures. And the surprising thing is that the temperature spikes are not near the boundary where the high flow times are, where he at first would have expected it. It occurs here in the center of the vortex, and then it says, okay, is it possible that this is due to high reaction rates? But when you look at it, the reaction rate in the center of the vortex is almost 0, so it's not really the reaction rate driving it. Flow time also looks fine in that region. So basically, what the conclusion that Ignaz gets to is it must be something with the discretization, because in this vortex, that's basically the most challenging region currently for the visualization. It's possible, for instance, that the flow field there is slightly has a non-zero divergence, and because of that, energy accumulates in there. But that's something that he can now keep on investigating. One thing to be aware of, I said that these function objects need a lot of time. Beware that you don't duplicate. Beware that each of these function objects does the copying of time steps on its own. So if you use a lot of them, you use a lot of memory. In further OpenFOAM, swak4Foam versions, I'm planning to improve this. Okay. So I'm going to skip over the VF options. Most of this stuff here is explained in other presentations as well. It's basically one interesting application here is that you can use it to FV options. You can use them to execute function objects at every time a FV option would be executed. The last thing that I'm going to is optimization. Ignaz likes to sprinkle his cases with swak function objects. There's a lot of output by the function objects to the console, and then people pass by his computer and says, oh, okay, there's all these output from your from Swak. Probably that's slowing down your case tremendously, and he has a hard time explaining to them, if the computation time is not proportional to the output to the console. If, for instance, if the pressure equation is solved, then usually that's just one line on the console, and that takes up 20% of a typical OpenFOAM or 40% of a typical OpenFOAM case. So he uses high-level profiling to tell people, no, the function objects only use 5% of the computation time. Go away, these produce results, and results are the things that we do CFD for. the difference between high-level and low-level profiling is usually people talk about low-level profiling. Low-level profiling needs a binary that has debug symbols, and then you need a special program, usually Valgrind or something like this. And this program executes your executable and looks into the executable and looks how often is each line of code executed. The advantage of this is it's very, you can look very detailed at it, but it's terribly slow. It's slower than regular debug binaries would be. And the thing I'm showing you here is high-level profiling. For high-level profiling, you tell the code, okay, start the timer here, end the timer there, record the time, and please print it out for me in a way that I can post-process. That needs almost no time. You can use it in production code as well if you do it correctly, and you get every time you're told, okay, how much time is spent where. The profiling support in OpenFOAM versions, in the free OpenFOAM forks, 2 of them support it, 1 doesn't. The foundation release doesn't support it. At the time when I developed this profiling stuff, I proposed it and it was turned down. Look in the message board for this feature proposal, why it was turned down. I still don't understand why, but okay. Foam Extend accepted it and it's included it long ago, and ESI also accepted it and included it a couple of years ago, and they have since refactored it a bit. But what these 2 implementations have in common is that they write the profiling information to the time directory in a subdirectory uniform and into a file profiling. Basically, in theory, you could patch the foundation release to use profiling as well, but I don't develop these patches anymore because I don't use foundation release for production nowadays. I basically use it only for porting swak4Foam. In the ESI branch, you have to enable profiling. You have to add this to the control tick. Then it does the high-level profiling out of the box. There are several things that are profiled out of the box to make it useful. One is the time loop itself. I think I've got only 10 minutes, but I'm going to manage. One is the time loop itself. Then the thing that uses most of the time in a regular solver, that's the linear solvers. These are profiled. The writing of the values is profiled. If you write out a lot of stuff, you'll be surprised at how much time this might take, even if you do it every 100 time steps. And the function object execution is also automatically profiled. That's why Ignaz can be very confident to say that his function objects are not wasting too much of this. Basically, profiling internally, it uses little objects that are called triggers. Basically, what they do is when the object is constructed, it starts a clock, and when the object is destroyed, it stops the clock, or the clock is stopped before. And these triggers are then if once it has stopped, it reports the value to a central database, and the triggers are organized in a stack. So if a trigger is running, if another trigger is started, then basically this trigger is a child of the upper trigger, and you can you get a hierarchy of times. And when creating a trigger, we're going to see that on the next slide. When creating a trigger, you at first have to specify a C++ name. That one has to be used, for instance, for stopping the trigger. And you also can specify a readable string that will show up in the reports. For instance, here, Ignaz adds to the time equation. He adds this time equation trigger that he adds up here. He doesn't have to end this one because it's here inside of this scope. And once the scope ends, it's automatically destroyed. So, and when it's destroyed, the time is recorded. And then he's interested in for instance, in the calculation of the excess temperature. So basically he adds a profiling, he adds a trigger here, and that trigger has to be explicitly ended. And that's basically all you need to know on how to add these triggers to ESI solvers or to foam extent solvers. You don't have to include any header files. I think in foam extent, you don't have to include any header files as well. So as I said, it creates a hierarchy of trigger. And so if of triggers, and if a trigger sees it has children, then it has a total time, but it divides the total time in the child time and in its own time. That's the time where no other trigger is running. And if you have interesting sections of code that have a high fraction of own time, then it might be of interest to subdivide them. But if you have not, then it's basically no time is used in that section, and you don't have to profile it. It's a very, very stupid idea, or not a good idea, to add profiling in the inner loops. Don't do something like this. If you have a for all loop or something like this, then profiling will work, but it will take a significant amount of memory, and it might be the case that you're more profiling the profiling than profiling your own code. If you need profiling in the inner loop, then you have to go through low-level profiling. And as I said, there are also, for non-developers, it's quite useful. For instance, if you say, okay, is it faster to have a CG solver and 123 iterations with that, or only 5 AMG iterations? Then with profiling, you can see, okay, in this case, the pressure equation takes 10% of the computation time, and with the CG solver, it takes 40% of the computation time. Then you say, okay, the AMG seems to be much faster. The instrumented solver you'll find here. And Ignaz now is not very happy with the results that he gets, because when you look at these files, that's a bit, I mean, all the information is there, but it's hard to read. So he turns to PyFoam, because PyFoam has a utility that can be used to deal with this profiling output. I'm going to go through this a bit more quicker. In its easiest form, you just tell it to, you say, okay, profiling info. In the current case, look for the profiling info at the time 0.05, and then you get this list. Basically, this shows you that the hierarchy, it's basically, it says, okay, the top is the application main that took up 100% of the time. That's no surprise. And its children are, for instance, the reading of function objects, the starting of function objects, and the starting of function object, blah, 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 has these sub things. Over here, you see then how much time was used in itself and how much time did the children use. You see how often the trigger was called, and it's broken down for you how much time was spent in this. That is a lot of information, and there's a lot of, yeah, almost non-existing things. So the first thing Ignaz does is it tells it, okay, use a threshold of 1%. I don't want to know about any triggers below 1%. Then he reruns it. Then he gets the profiling information. Now that's much more interesting. For instance, now he knows, okay, the time equation, for instance, it takes 15% of the overall time. That's how much it is used there. Unaccounted for is 2.6%. And then you can look at, okay, and who is using the most time inside of the time equation. You can look at these here. And it turns out that most of it is used in VF option constraint time, which I stupidly switched on. So basically, by switching that off in FV options, because I'm not using it anyway, I could save 5% of the computation time. That's valuable information, I would say. And the execution of all the other function objects takes 5% of the overall time. So that's, I mean, you can save time here, but I think it's worth it. That's not quite easy to read, and it's not easy to put on slides. So basically, in the latest PyFoam version, it can generate graphs for you. Basically, what it needs is the dot utility of the graph viz suite. That's the graph viz suite is used in half of the Unix utilities that generate graphs. So it's a good chance that it's already installed on your machine. And basically what you say, you give it the regular output, you then say graph with dot, then it generates something that dot can read. So you put the pipe here and you pipe it into dot, and then you can give it the regular options. Here, for instance, I generate a SVG file. The advantage of SVG files is that's a vector format, and I can load it into my web browser, have a look at it in the web browser like this. Basically, you see here, this has this child node. The child node needs, so basically, the nodes are colored according to the time that they use themselves, and these arrows are colored according to the amount of time that is spent there. So basically the most of the time is spent over here. And as I said, you can zoom in your web browser and can have a look at it more in detail. You see here, okay, that the pressure equation takes 30% of the time, which is the regular operation for the pressure equation. So I'm coming to the conclusion. Ignaz says goodbye. He says he hopes that you've learned how to do this thing, to use these things for development, especially rapidly switching between versions, getting crash dumps from cases, and find sections that where, for instance, the performance needs improvement. And he now gets back to his combustion model, and he hopes that we don't talk about his combustion model anymore. Here, if you found this interesting, there's a couple of other presentations that I gave at other workshops that you can have a look at. And so, yeah, thanks for listening. Questions? Yeah, this presentation is under this license. I look at the, I just have to refresh it. There's two questions. One of that says it's useful. Thank you very much. And the other one, okay, sorry, now the web browser, just before I started reading it, the refresh started. Just 1 minute. Yeah, but okay. Now the question has this. Okay. At some point, do you need to directly call OpenFOAM functionality from Python or vice versa? If so, in your opinion, what's the best approach for that? Well, directly calling OpenFOAM functionality from Python, no, I don't do that, and it's a bit hard to implement this. There used to be another PyFoam project that tried to do that. That was something similar to what Herf has shown you in his keynote speech. There is in swak4Foam. swak4Foam has swak4Foam has a functionality to call Python programs from swak4Foam. But this is a bit experimental, and it's hard to get used to. But if you want to, you can give it a spin. There are also, I think, if you Google for that, you will find some things for that. Yeah. Yeah, but to get back to this Python question, yeah, I mean the approach to do that, you need a so-called wrapper library or wrapper generator. It's a lot of work, and I don't know if it's worth the effort usually. Okay, so thank you very much. I think the time is up. No more questions here. Feel free to reach out to me during the conference. Yeah, thank you very much, and have a nice conference.